Hi there. So my name is Scott Davidson. I'm a graduate engineering geologist at Mont Macdonald, Cambridge. I'm going to talk to you about the Devoll hydropower project and how I added value for identifying risk and opportunity. So just to lay the presentation out for you, I'll just give you the background, regional geology tectonics, and the location. So Banyan Dam, I'll give you an overview, talk about the ground model, the risks and opportunities at that site. I'll do the same process again for the access roads to Meglice Dam, and I'll wrap up with a conclusion. So, by way of introduction, the Devoll hydropower project is a cascade of 2 dams in central Albania on the Mediterranean, just above Greece and across from Italy. Statkraft is a Norwegian state-owned energy company. In 2008, Statkraft signed a concession with the Republic of Albania to build, own and operate the project for just over €500 million. The project will represent a 17% increase in Albanian power generation and produce 729 gigawatt hours annually. Statkraft set up a local company called DHP. DHP will operate and sell the electricity to the international market and administer the design and build contract. Now, DHP appointed a joint venture between Mont Macdonald and Coin & Belliere as owner's engineer for Banyan Dam, their transmission lines, the access roads to Meglice Dam, although the joint venture was not involved in Meglice Dam itself. Construction began in 2013, with the access roads and transmission lines completing in 2015. Banyan Dam officially opened and is kicking out power as of a month ago, and Meglice Dam is due for completion in 2018. So now to touch upon the regional geology and tectonics of the area. So the African plate is interacting with the Eurasian plate in the Mediterranean, which is creating a compressional stress regime forming an alpine Mediterranean mountain belt. The belt can be subdivided into north-northwest, south-southeast striking units. So there are 3 zones in which you're interested, which is that black box in the center of the screen. So from left to right, in orange, we have the Kruger zone. Now, the Kruger zone is a middle to lower Oligocene flysch. The flysch originates from a deep marine foreland basin and is highly folded and faulted mixture of mudstone, siltstone, and sandstone. Banyan Dam is located entirely in this unit. The aquamarine area in the middle is the Medita zone. It's a Middle Jurassic mantle ophiolite, which is a rare assemblage with limited documented engineering precedent, which is interesting when you compare it to the information available on the London clay. So Meglice Dam and the access roads to it are located in this unit. Finally, we have the pale green area on the far right of the box. This is the Krasta-Kakali zone. It's a Middle Eocene flysch, and parts of the access roads are located in this. The Kruger zone is overthrust by the Medita zone, which in turn is overthrust by the Krasta-Kakali zone. I was part of the Banyan engineering geology team of 3 geologists. I was led by an Italian senior geologist, an Albanian graduate geologist, and myself. I joined the team in early 2014 and was with them for 7 months. So the idea of Banyan Dam is not original. The dam site was partially built and abandoned in the 1970s due to a lack of funds. DHP arrived in 2008 and wished to generate 70 megawatts and 254 gigawatt hours annually. To do this, the designers, AF Consult, had to utilize a head of 80 meters and a reservoir capacity of 400 million meters cubed to drive 2 Francis turbines in a buried powerhouse. So the first attempts left behind a partially constructed clay core, an earth embankment cofferdam, and a grouting gallery. As you can see from the difference in 2009 to 2014, a lot of work was undertaken. So to achieve the 80-meter head requirement, the original dam size was increased to 80 meters in height, 900 meters in length, and 370 meters in width. The ancillary structures are not small either. The spillway is 378 meters long, 24 meters deep, and discharges into a stilling basin 106 meters long, 14 meters deep, with a total cut height of 53 meters. So these photos are before and after of the powerhouse excavation. The powerhouse there was excavated to 44 meters. So now to touch upon the ground model at Banyan Dam. As I mentioned before, the dam is located in the Kruger zone. The flysch forms the bedrock to a 1 kilometer wide fluvial valley, in which there are multiple benches of river terrace deposits associated with the tectonic uplift of the valley. As can be seen in this model, the bedrock is reverse faulted and highly folded, both on the macro and the micro scale. So, here in the photo of the Quaternary deposits, the bedrock is capped by 6 meters of river terrace deposits, which have themselves been capped by up to 2 meters of alluvium. Now, colluvium could also be present, but was typically found in areas of no terrace deposits and could increase locally to 10 meters thick, depending upon weathering. Groundwater level was typically very low and tied into generally above the river level. However, seepage was very common in the slope faces. Quaternary deposits typically had to support slopes of about 1 vertical, 2 horizontal, which is roughly 27 degrees. Now, the Fleece bedrock is typically highly weathered for about 2 meters before becoming fresh to slightly weathered. Now, the design needs to fit very large structures within the site, and hence permanent slopes of 2 vertical, 1 horizontal, or 63 degrees, and 8-meter height were required. The dam shell itself requires Fleece foundations to be a minimum moderately weathered into weak rock, which is about 5 to 25 MPa. The core and critical structures require slightly weathered and medium strong rocks in the region of 25 to 50 MPa. Now, Fleece was mapped to GSI, which was related by the designers to a custom slope support. Good GSIs, things like in sandstones, about 55 to 65. In the worst case, we had highly folded shales with GSIs from 10 to 15. Typically, we're looking at GSI of about 40. So that covers the background of the site. I shall now talk about my experiences on the dam site. So, risk and opportunity. How did I define my risk? Just using a standard 5x5 quality of risk matrix table, where likelihood is scored from improbable through to frequent, and severity is defined by impact, cost, time, reputation, health and safety, and environment. So, the geologists were organized within the engineer so that we had direct responsibility to our construction manager and direct contact with the designer. Now, the designer had no presence on site, and hence, as part of the risk mitigation strategy, the observations of the site geologists were critical to feed information back to them for large design amendments. But the smaller changes could be handled within the engineer's role. The typical role of the engineering geologist on this site was to instruct permanent slope support, approve temporary support, and to approve the foundations. The main hazards I will discuss are slope failure, surface water management, soft spots, and sulfuric water. So, given the highly variable nature of the Fleece and the various geometries cut into it, slope support was always going to be a bit of a hot topic, with a high likelihood of failures and the associated impacts resulting in a high risk. The subject clearly requires an engineering geologist to be present on site to help mitigate the risk and forestall progressive slope failures. In this scenario, the exposed Fleece was dipping into the slope face, and the contractor applied the standard shotcrete blinding for temporary support. However, just beyond the slope face, the Fleece became closely jointed and folded so that it dipped back out of the face. The face subsequently failed, and I had to advise the contractor to apply a permanent support class to reduce the likelihood, as further shotcreting would just have resulted in further failures. Now, the original design called for angular edges to burns, but given the observed behavior of the Fleece, the lead engineering geologist instructed rounded corners which improved stability. I then took this principle forward and I applied it to all subsequent slope excavations. The dam site sits in a rainy environment, and so surface runoff is a big problem. A ditch was dug along the top of a berm, but it wasn't lined. This meant that the surface runoff would focus in the ditch and move into the soil, reducing its effective stress and leading to movement. So here we can see some of those small movements as a result of that lack of lining. I recommended the lining of these ditches either by shotcrete or plastic lining, and did it as soon as possible, and it was quickly implemented. Now, the likelihood of movements caused by poor surface water management is high, which would have had a high impact, and therefore we had a high risk. The likelihood was dramatically reduced by adding an impermeable liner to these ditches. In this photo, we can see local weakening of Fleece, in which I've sprayed red zones around it to be excavated by an air lance. The likelihood of encountering these weak rock scenarios is medium, and the impact and risk high as a result of the cumulative additional program and material backfill costs. In this scenario, an excavation was taking place on the spillway. Slightly weathered Fleece can be seen on the left, and a completely weathered Fleece on the right. The design assumed it all to be rock, and that the foundation would be on the red line, but due to a likely higher hydraulic conductivity, a deeper weathering profile emerged. As a result of this, we had to excavate and reconstruct with mass fill concrete. This is one of the key areas for a geologist to look at. The contractor was planning on excavating to that bottom blue line. However, on close inspection of the rock, I was able to discern that excavating to the yellow line would be acceptable, meeting our design requirements. This allowed the contractor to minimize time and material on backfilling it with mass fill concrete. In one local area, I found sulfuric water, which nobody else had spotted. To a geologist, it was obvious given the milky water and smell, but to non-geologists, it may just appear as dusty water. As a result, I asked the structural engineers to switch to a suitable concrete class, avoiding the use of limestone for concrete aggregate in this area. The likelihood of this occurring site-wide was low, but the impact to structural integrity of concrete was high, and therefore risk is high. So now I'm going to summarize my experiences in terms of risk and opportunity. Through the efforts of myself and my fellow geologists, we were able to reduce the risks of slope failure from high to medium by tailoring the designs. We also closely examined the weak rock to reduce over-excavation. I personally oversaw the surface water management on sulfuric water risk mitigation. So now to touch on the access roads for Meglice Dam. DHP wished to build a 172 megawatt, 475 gigawatt hour output annually in a 460 meter wide, 150 meter high asphalt core rock-filled dam at Meglice. With an 11 kilometer long head race tunnel, feeding a downstream underground powerhouse and switchyard built on canyon slopes. To facilitate the construction of this, 34 kilometers of access roads had to be built or upgraded, of which 10 kilometers was in a canyon. So before you can build the dam, you need to build the access roads. The main road requirement was for oversized vehicles, such as long loader transporting turbines, transformers and machinery, to be able to make these tight canyon turns. This required the construction of retaining walls, bridges, culverts, and slope support. Here we see a photo of the canyon before construction works and after. As you can see, it's a significant improvement. So just to touch back on that ground model again, the road sits within the orange Krastika-Kali and the aquamarine Medita zones, which are fleesh and ophiolite respectively. As mentioned before, the fleesh is a highly folded and faulted mixture of mudstone, siltstone, and sandstone, which originates from a deep marine falling basin. The ophiolite is from a section of oceanic plate thrust to the surface. Here we can see the body of the ophiolite, which forms the canyon, and you can see the thrust faults, which define the boundaries between the ophiolite and the fleesh. At Banya Dam, we had permanent slopes of 63 degrees and 8 meters height in fleesh, whereas at Meglice, the fleesh had to sustain permanent slopes of 45 degrees to 72 degrees, depending upon the slope geometry. The ophiolite primarily consists of a serpentinite version of basalt. It's a slightly weathered and extremely strong rock with 3 main joint sets plus random, which tend to be closely to widely spaced with occasional seepage. Within the ophiolite, a cut face of 79 degrees had to be sustained to balance the steep slope faces with a 2-lane width requirement. The contract was designed and built with Italian designers, and the joint venture again was the engineer, but we also provided an additional design review capacity. I was brought in as the sole site engineering geologist to collect and analyze canyon data so that it could be compared to the design. I spent 3 months on site collecting the data before handing over to a colleague and returning to the UK. I'm going to pick up on 2 of the main hazards with a focus on the canyon area where I spent most of my time. The principal hazard to roadwork construction is slope failure, as this could cause injury, fatality, damage machinery and foundations, and could delay the works. Given that there were 3 main joint sets plus random joints, and roads that changed their slope face orientations as they snake around through the canyon, critical slopes were to be expected. So I had to collect and analyze data for the comparison with the designer for 10 kilometers of canyon road. I decided that the best way of doing this would be to create a record of the existing alignment, so I sat down with the contractor to discuss what his priority areas were. I would then take photos of the entire section, place them in PowerPoint, and annotate them so that the check and approvers in the UK would be able to see exactly what I was referring to in my analyses. I then developed a technique that would allow me to record useful data about the entire alignment for the purposes of running a back analysis on any failures and to help assess potential for future ones. I call this SDMR, or schematic data mapping ribbons. Now this recorded useful data such as vegetation, gullies, rock type, weathering, strength, failure modes, directions and resultant block sizes, joint openness and groundwaters. I'd also make comments on if the placement of the rockfall barrier, slope support or retaining walls could be extended, shortened, removed or relocated. I found that in some cases I was able to significantly reduce the support and others where it would be advisable to increase it. In one location alone, I was able to cut 15 meters of retaining wall out of the design, saving material cost and program. The cost of a single 3 meter high, 1.5 meter wide retaining panel is about €50. So there you're saving €750 in material costs alone. As part of the design, I So I would do a full analysis of the designer's type sections, where I would measure RMR, which had been chosen by the different designers instead of GSI, because it's relatable to slope tilt measures, and if recorded, the component data allows you to run a kinematic analysis. This is in contrast to Banya Dam, where GSI was principally used. RMR at the access roads was in the region of 60s to 70s, which is good rock. To aid the design review, I also recorded the additional parameters required for Q-system, such as joint set number. Initially, I was doing the kinematic analysis by hand until a software package called DIPS was made available. As you can see here, a planar failure is possible, a topple may occur, and we are at the limit of wedges. I would then take the data and feed it into a wedge failure software package called SWedge. So I'd run the slope factor of safety analysis for the current existing slope face and the proposed design face using a combination analysis and seismic loading. In this case, a factor of safety of 0.18 was apparent, and we advised the designer to amend his design. Where existing road cuts were noted to have a low factor of safety, the contractor was notified. So now I'm going to touch base on a few more scenarios for risk and opportunity. Whilst managing the road cuttings in the Fleece, I was mindful of the challenges I faced at Banya Dam. I was keen to relate my experiences from the Banya Fleece to the Meglice roads, where some of the cuttings began to fail downstream of the Meglice Dam. I identified, mapped, and characterized the failures with my team and provided remediation suggestions to the client and designer. The principal failure mechanism here was judged to be circular and caused by too steep a slope face, in addition to no water intercept channels at the top of the slope. This guided our suggested remediation solutions towards combinations of slope reprofiling and surface water control. It was decided by the client that allowing the gradual slope failures and performing maintenance would be their optimal compromise. Now, given the variability in weathering of the Fleece, the likelihood of failures was high. The impact was also high. For example, a good-sized slip could close the road down, impact your program, and impact health and safety. For example, by cutting off the emergency services. Therefore, the risk was high. A lot of foundations were being put into the road alignment, be they new bridge abutments or retaining walls. The foundations need to be checked for bearing capacity, soft spots, and excavation stability, especially since live work traffic was running over the top of the slopes, or static loads, in the case of the crane in the top left of that photo. This activity had a medium likelihood and a high impact, giving a high risk. So now I'm going to summarize my experiences again in the context of risk and opportunity. My job was to reconcile the design with the ground reality and variability. I succeeded in reducing the risk for both these hazards. I was able to reduce the risk of slope failure from high to medium, but I can't call it low until the support has actually been installed, although it has now been installed, so it's low. There's, of course, a residual risk for those obscured random joints or changing geology behind a slope face, as I highlighted in the Banya powerhouse earlier on. Through my actions, I was able to forestall, delay, tailor the design, ensure quality, and minimize the contingency expenditures. So now I've come to the conclusion. There was a high degree of cultural diversity within the project team. So as well as variability in the ground, I also had to manage communication and collaboration between Albanians, Italians, Brits, Norwegians, each with their own philosophies, and we had to achieve some sort of consensus. Fortunately, we were all working to Eurocode 7. There's a huge amount of potential for variation in the ground model, coupled with large and movable complex structures, which require a mixture of temporary and permanent design. The designer was not present on site to adapt his design to the encountered conditions, and so this was my job. I achieved this through being present on site and using my core engineering geological skills of mapping, field tests, discontinuity analyses, and the power of observations and reasonable deduction. Through this, I was able to reduce risk, make contributions to keep the program on time and with minimal contingency expenditure. Though I was the only geologist on the roads, I was also part of a great team of geologists doing similar things for other elements of the scheme. So in absolute conclusion, the role of the geologist is absolutely fundamental to the management of risk, successful delivery of the construction. Thank you for giving me this opportunity. I'd like to invite any questions.